Okay, I have a little example up here. Don't overthink it. There's nothing supposed to be super profound. Just an observation I want us to make so that you have an intuition for these definitions. If I take a times my vector u, then I have 3, 1, minus 2, 0 times minus 1, 1. And if I do that, I get minus 5, minus 1. Okay, so nothing crazy. That's literally just multiplication. We've been doing that. Now what about a times v though, right? If I did a times v, I have 3, 1, minus 2, 0 times 2, 1. And if I take that product, I spit out 4, 2. Here's my question to you. Do you see a relationship between the vector v and the vector a times v?
2x.
Yeah, it's 2 times. Right? This is actually just a scaled version of the vector v. Now it's not like that's kind of interesting because that's not typically what we'd expect. Like this output has absolutely no relationship whatsoever to its corresponding input vector. And so with respect to this particular matrix A, this is a very special vector. Corresponding to this specific matrix, there's some sort of a vector that once I transform it, it's actually just a scaled version of itself. So visually, what does that mean? Well, if I had a plane here, 1, 2, 3, then the vector u is minus 1, 1 to start. So minus 1, 1 to start. So this is where u is to start. Minus 1, 1. And then after it gets transformed by a, where does it get sent to instead? Minus 5, minus 1. So 1, 2, 3, 4, 5, minus 1. So we get sent down here. So this is the vector a times u, which is minus 5, minus 1. And so, effectively, A, the matrix, sends a vector to something that is on a completely different span, okay? Now compare it with this. The vector V is 2, 1. So we start at 2, 1. So here's my vector V. But even after transforming the space, instead of getting distorted and pointing in a different direction like the first one, we actually end up just elongating out drawn exactly to scale, as you can tell. 2, 4, 2.
So nice.
Okay? It's on the span of that original vector. Okay? So this tells us that sometimes when I have a matrix, there are types of vectors that don't get affected directionally. They end up being on the same span as what they were to start. This is what we mean and care about when we talk about an eigenvector. Okay? So to be an eigenvector, you can think of it as kind of like a directionally unaffected vector if you were to multiply it by the specific matrix. So I'll articulate this more clearly in a definition statement. But I just wanted to show you that example because it's a very easy computation, but it kind of visually gets our intuition in the right direction. An eigenvector of an n by n matrix of an n by n matrix A is a non-zero vector, such that, well, we can call it x so we have a way to reference it. So vector x such that A, so my matrix A times x, transforms it, and it's in the same span of x. So some lambda, this is a scalar. Bless you. Lambda x for some scalar, scalar lambda. Now, we have a special name for this particular scalar as well. A scalar lambda is called, you could probably guess just based off the section title, is called a what? Yes, eigenvalue of the matrix A. If there is a non-trivial solution, non-trivial, we've talked a lot about that. Gee, couldn't have any barons on n by n matrices. A, it will. Non-trivial solution X of, and then again, here's this equation. Ax equals lambda x. And then we also have, we can say such in x is called an eigenvector corresponding to lambda. So this is tedious, but necessary because now you'll never be confused what's being referred to. So if I'm saying I want an eigenvector for this eigenvalue, but that's different than this over here for a separate eigenvalue, now we have a language to talk about when I want eigenvectors corresponding to which eigenvalues, etc. Okay, so over here is the vector u an eigenvector?
No,
Why not?
because it doesn't x. When you multiply it by a, the result is not a scalar times u.
Yeah, once I transform it, there's no way for me to just slap on a scalar multiple that connects it to its output. Okay, is v an eigenvector?
Yes.
Why is it an eigenvector? Yeah, basically, if I transform it, the resulting vector a times v is just some sort of scalar multiple of the original starting vector. What do I call the number 2 in this specific instance? An eigenvalue, right? So, I could say that v is an eigenvector corresponding to 2. Okay, so that's kind of how we tie all the language together. Yes? No? Alrighty. So then I'll go to this example. It can be helpful to, I'm going to leave this definition up here actually. Just for a little bit longer. We're going to show that the number 7 is an eigenvalue of the matrix A is equal to 1, 5, 6, 2. And then we're going to find the corresponding eigenvectors, right? An eigenvalue is always going to be accompanied by its eigenvectors. In a similar sense, if you have an eigenvector, it has some corresponding eigenvalue. Find the corresponding eigenvectors. Okay, so here's how we do that. The very statement itself that 7 is an eigenvalue that very statement logically implies by definition that AX is equal to 7x. Basically, there's going to be some non-trivial x that satisfies this relationship. 7 is the scalar. So instead of the unknown, the previous example, the unknown was the eigenvalue. We were given the vector and then asked to figure out what the corresponding scalar multiple is. This time it's the reverse. They're telling us straight up what that scalar multiple is, and now we're interested in what the original x is. And we're guaranteed that this has a non-trivial solution. Again, foreshadowing that definitely has no bearance on anything whatsoever. A matrix equation having a non-trivial solution.
It's not invertible.
Okay, so let's just solve this. I'm going to get this on this side, so I take AX, I can subtract 7x from both sides, and so there's 0 vector over there because I'm handling vectors and matrices. And so notice, here's what you're going to need to know. This is kind of the not so obvious thing that can feel obvious once you see it. But if I'm going to factor out these matrices, what did I insert between here and here? Identity. Why do I need that identity? Well, because if I'm going to factor out the x, is what type of an object is A? What type of an object is 7? Can I treat those as the same type of object? No. So, but what does introducing I do here? To a matrix. Does I change the actual value of the x? No. So this is the little trick here, to convert my scalar representation to a matrix, to treat it and factor it. So now I can actually factor out A minus 7i, and then have the x on the outside. Yes? And when you really think about it, then you step away and realize that A minus 7i is in itself just a matrix. That's really easy to figure out, right? Because let's copy and paste what A is. A is just the 2 by 2, that's 1, 5, 6, 2. That's A. Minus 7 times, and then the identity in 2 by 2 is just 1, 0, and then 0, 1. Still have our x out here. Okay. So I mean, kind of like big whoop, right? So whenever you multiply a scalar by the identity, all of the ones just get scaled up to whatever that scalar was. So it'll just be 7, 0, and 0, 7. So I'll just have, I'll just have 1, 5, 6, 2 minus 7, 0, 0, 7 times x, 0. So what is that matrix actually going to be? What's 1 minus 7?
Negative 6.
And then 5 is unaffected, the 6
5.
is affected. 2 minus the 7.
Negative 5.
Back to chapter 1. Okay, this is just a matrix equation. And if you are particularly astute and have been doing a lot of row reduction, you'll immediately recognize that this will produce free variables. This is going to clear out to a bottom 0. How do I know that for sure? Well, it's because this matrix equation is equivalent to this augmented matrix. Minus 6, 6, and then 5 minus 5, and then 0, 0, because it's a homogeneous equation. Which if you do R1 over negative 6, returning that to R1, and then scale R2 down by 5, and returning that to R2, then you will get 1 minus 1, 0, 1 minus 1, 0. Whenever you have duplicate rows, the lower one always goes. It's just going to be 0, and so that's communicated through R2 minus R1 being returned to R2, which will give us 1 minus 1, 0, 0, 0, 0. Okay? I'm not concerned about you knowing how row reduction works, because again, that's just doing the arithmetic from chapter 1. And then, if not, what does matter here is how we represent the solution. So the solution is that x1 minus x2 is 0, and that x2 we call what?
Free.
Free. So if I'm representing the vector x as a general solution, x1 and x2, what do I put in for x1?
X2.
Yeah, I just put an x2 because I put it over, so this is x2. And if x2 is a free variable, what does that mean I do to its actual partner? It's himself, it's just x2. So now, what's always the next step after making that substitution?
Factor out.
Factor out what you can. So we factor out x2, and I'm left with what vector?
1.
1, 1. Fantastic. And because does it matter what the x2 is? No, so it's effectively every single linear combination of this vector, which sounds a lot like which concept? Span. So the span of 1, 1 is going to give me all the possible solutions to this matrix equation. And this matrix equation is the same exact matrix equation as this one. Okay? So this is telling me that the span of 1, 1, any vector in this span is going to be a non-trivial solution corresponding to the eigenvalue of 7. Okay? So, let's see.
Will this be true for anything that has 2 that add up to the same and 2 that add up to the same? So if they added up to 6 and 6, it would be an eigenvalue of 6?
That's coincidental for this example.
Okay.
Yes. Nice pattern recognition, unfortunately coincidental. There is another pattern that's, again, associated with diagonals. Matrices really like echelon forms and diagonals on echelon forms. It's like it repeats itself over and over again. Okay, so there's that example. Understand, be able to do that. But let me do a definition because it'll kind of summarize this example. The key strategy here is recognizing that even though we've introduced a new definition and a new concept, the procedure ends up being the construction of just a matrix equation. And since it's just a matrix equation, everything you already know about matrix equations transfers. So math classes in some sense get easier over time because you start just repeating the same tools in different ways. So the set of all solutions of all solutions of this particular equation, right? In general, you could always get to something that looks like a minus your lambda I times the vector x is equal to 0. Irrespective of which starting eigenvalue you're given, the algebra is always going to turn into that if you do the factorization every single time. So we just kind of start with that. This is just and you know the answer to this, so I'm going to give you a second. A minus lambda I, that whole thing, once you simplify it, what object is that simply? It's just a matrix. I have a matrix, even though it looks kind of funny in notation, that's just a matrix, times my x, set equal to the 0 vector. What type of equation is this? Okay, and so in chapter 4, what special name did we give to the solution set, all possible solutions to the homogeneous equation? The null space. So the set of all possible solutions here is just a type of null space by definition. So this is just the null space. Of the matrix A minus lambda I. So this set is a subspace. Why do I know that it's a subspace? What did we take the time to prove about null spaces in general? All null spaces are subspaces. So of course this one also is a subspace of Rn. And we give it a special name. and is called the eigenspace. Eigenspace of A corresponding to lambda. Okay, so in case that wasn't inherently super obvious, recall from chapter 4 that in general, a null space of some matrix A is essentially all the solutions X in Rn with one condition, is that so long as that vector gets sent to the 0 vector, then it counts. So now say I want to think of, basically just think of the whole A minus lambda I. Just think of that as some other matrix. It is ultimately just one matrix when you simplify it, okay? Then all we're saying is, okay, well, null space of B is all the vectors X in Rn such that B times X is equal to 0. So we have no issue with viewing a matrix as a single symbol. So we all can start extending our understanding to a broader type. So if I actually represent it this way, vectors X in Rn such that A minus lambda I times X is equal to 0. Is everyone seeing what I mean by null space now? It's just an issue of perspective, whether you view the A minus lambda I as actually just one singular object, then this is going to come for free. Okay. Oh, we're doing swimmingly. Okay, fantastic. I want to be able to spend some time on this because this is helpful. Okay, how do we feel about the definition of eigenvector, eigenvalue? Here's a hint. Eigenspace is a null space. Boom. You're studying nothing new, so everything you know about null spaces is going to be translatable to eigenspaces. So don't think that this is like suddenly, oh, time to memorize a whole new chapter, whole different concept, whole different, nope. An eigenspace is a null space by definition. So, remember when we did the procedure and broke down step by step, the bare minimum required steps to get a basis for a null space? So if Pearson says, hey, give me a basis for an eigenspace, we don't freak out. Because what do we remember? Oh, eigenspace is definitionally just a null space. So as long as you figure out what the matrix is that you're doing the null space of, the procedure is copy-paste from skills you already have, okay? So the way I'm presenting the material in lecture is to minimize the amount of stuff that has to be done new, okay? Don't relearn stuff that you already, don't reinvent the wheel every single time you do a problem. There's a very fine line in undergraduate math textbooks between repeating itself, not for the sake of redundancy, but for the sake of not assuming the student can abstract more than they are able to at the moment. So in higher algebra studies, all of these kinds of spaces and definitions kind of get lumped and unified into a higher structure, structures that all share these same exact properties and procedures. So it'll feel a little bit repetitive, but it's just the nature of the game. Okay, so here's kind of a slight summary. Since an eigenspace is just a null space, the procedure for finding a basis. Finding a basis for an eigenspace is no different than for null spaces. As a means of review, because that one lecture was pretty handy in summarizing stuff, what is the very first thing you do procedurally if you need to find the null space of a specific matrix?
Reduce to row reduced.
Yeah, we're going to row reduce this sucker all the way to row reduced. What if I only wanted the column space? Where do I stop? Just an echelon form is fine. But, so if an eigenspace is a null space, and I want a basis for an eigenspace, how far do I need to go? All the way to row reduced. Okay? So if you do it in part of the procedure for null space, you will do it for the procedure of an eigenspace. It's exactly the same thing. Okay? So that's my disclaimer. It should not be different. When you're doing your problems and you're finding a basis for an eigenspace, it shouldn't look different than if you were doing a null space, for the reason that it in itself is just a renamed null space. Okay?
Why do we have eigenspaces then?
Hmm?
Why do we have eigenspaces if they're just renamed null spaces?
Well, we take advantage of the fact that null space is a broader concept, so now we're looking at specific types of null spaces. And using null space is going to give us statements about the invertible matrix theorem that are otherwise non-trivial if we were only to look at the definition of eigenvector. Okay. So we'll have a way to relate eigenspaces, eigenvectors, and the outputs to invertible matrix theorem. It's going to give us faster shortcuts to check invertibility, etc. And then there's also going to be ways to do something we would call diagonalization that come through this. Okay. So yes, we will do new stuff in the chapter. But I'm showing you that the foundation of it mechanistically is the same. So it's not like a completely different genre of stuff. Okay, so the eigenvalues, and this is kind of a fun callback to chapter 3 with the determinant shortcut. The eigenvalues of a triangular matrix. Question. Triangular matrix. Notice that it's not specified if it's upper or lower, which means it's both. Are the entries on its main diagonal. And instead of just memorizing this shortcut because you can, this is a really, really intuitive visually. This is one of my favorite shortcuts. I'm not going to do a formal proof of it. Let's just do a 3x3 case example. Let's say I had wanted to find the eigenvalue of some vector, or some matrix A. Well then, I know I'm going to eventually end up needing to know what my A minus lambda I is. Okay? And so, if I'm doing the 3x3 case, then I just have the entry here that's A11. Since it's triangular, I know that underneath that pivot it all needs to be 0, so it's 0, 0. This A12 could be anything. And again, if we've forgotten the indexing, the first index is always the row, and the second index is always the column address. So what this is telling me is first row, first column. First row, second column, etc. So this here would be second row, second column, A22. And then first row, third column, second row, third column, third row, third column. So there's my A in a 3x3 case, minus lambda times I. And since I'm doing 3x3, I will put my identity as such. So I'll do 3x3 identity. Okay. Well, I know that this is always going to look like replace all of my ones with the lambda. So lambda times I is really just the matrix lambda 0, 0. 0 is 0, lambda 0. And 0, 0. Lambda, yes. Because now when I subtract these from each other, I have A11 minus lambda, because the corresponding entries are going to subtract 0, 0. And then I have 0, A22 minus lambda, 0. And then I have 0, 0, A33 minus lambda. And just the way that identity matrix is visually already lets you know the only things getting affected in this entire subtraction are only diagonal entries. So that should immediately cue us into intuitive reasoning for this theorem. Okay, that only the diagonal entries are being affected here by this minus lambda I action. And when I do so, suppose any given one of those lambdas are the corresponding values. So say I take lambda is equal to A11. What is that value going to simplify to? 0. You know, there is a very, I typoed here. This is still unaffected A12. This is still A13, and this is still A23. Sorry about that. The key here is I will suddenly have a 0 in a pivot position. And what we know from the invertible matrix theorem, if I put a 0 into a pivot position, what type of a variable do I introduce?
Free variable.
A free variable. Can I be invertible with free variables?
No.
No. Okay, so this is going to say some stuff. Also, well, I don't want to get too ahead in the other lecture. The next lecture is going to talk about these relationships. Basically, if I have eigenvalues that correspond with the main diagonal, if you make your matrix not invertible, then we might want to include that on the IMT. Okay, but does the intuition here make sense? Subtracting this specific lambda I from any given matrix will always only affect your diagonal entries. And if it's affecting only your diagonal entries in such a way that it's the diagonal entry subtracted by that very lambda, then yes, I would presume choosing the very specific thing to force the existence of a free variable is going to introduce problem. But the nice thing about introducing free variables is what do the existence of free variables do for us with respect to null spaces in general? So if I have a homogeneous equation, I'm going to use a different symbol just so it's not confusing. Okay, so if I have a homogeneous equation, what happens if the only possible solution is just the trivial solution?
There's no free variable.
No free variables. And along with that comes all of the statements. The columns of B are linearly independent, blah, 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 right? So if I then say to you, okay, B, x equals 0, this does have non-trivial solutions, what does that immediately tell me? I have free variables. But basically the null space has stuff in it.
Yeah.
Right? What it means to be a solution here means you're a member of the null space. So if I only have the trivial solution, then what's in my null space?
0.
Just the 0 vector. If I have free variables, what's going to be in the null space? All the span of the free variables. So by forcing the existence of free variables, which is effectively what an eigenvalue does to my matrix, I have forced the existence of stuff that can be spanned to make a null space. In other words, I'm guaranteeing that there will be things in my null space beyond just the trivial solution. Okay? So the existence of free variables means that we're going to have non-trivial solutions. And then if I have non-trivial solutions, then that means my null space has infinitely many vectors. Okay? So that's what we want with these eigenvalues. You could think of those diagonal entries as forcing free variables so that we definitely have to have non-trivial solutions to the corresponding homogeneous equation. Because that's going to make our eigenspace have stuff in it. Otherwise, the eigenspace is empty. Okay. So practically speaking, suppose you're given these two matrices. Suppose you're given the matrix A is equal to 3, 0, 0, 6, 0, 0, minus 8, 6, 2. And maybe a different matrix B is 4, minus 2, 5, 0, 1, 3, and 0, 0, 4. Okay? So the eigenvalues of A, are what?
3, 0, 2. 3 and 2.
First question, is A triangular?
Yes.
Yeah, it is. Don't forget that triangular matrices are allowed to have 0 entries on the diagonal, right? So then the main diagonal is this, right here. So every single entry on that main diagonal is going to be an eigenvalue. 3, 0, and 2. Okay, what about the eigenvalues of B?
So 1.
Yeah, so we go down the main diagonal. Why am I allowed to take just the diagonal? Because it's triangular. So I have 4, 1, 4. I will get into more why I'm listing 4 twice here. The word we use is multiplicity. Its multiplicity is 2 because it occurs twice. And that's going to matter for the algorithm in diagonalization. Okay, so for now, just trust the process. If you have repeated eigenvalues, then take note of that. That's very important information to the matrix itself. Okay. Questions about how to read a triangular matrix for eigenvalues? I mean, again, it's one of those point and shoot things. It was kind of like with the determinant. If you have a triangular matrix and you want the determinant, there's not a lot of genius to just slide down the diagonal and multiply everything, right? Same sense here. It's not a lot of genius to just look at the diagonal and take those values. Okay. So let's get on to, perfect. Just 2 more little things. Because this will help set up the discussion for Wednesday. Have any of you thought in any of this time, what happens if 0 itself is an eigenvalue? Right? Because when you really think about it, that looks kind of funny. If I end up with something like ax is equal to 0 times x, because that's technically a scalar. But then you might be thinking, well, isn't 0 times x just the 0 vector? So what on earth is going on here? Especially like here, this matrix A, one of its eigenvalues is 0. Okay, what do we really mean by that? Because obviously I'm not visually scaling anywhere, so what happens? Let's take a look. So if I have 0 as an eigenvalue, of my matrix A, this is where knowing the full definition is going to become apparently obvious, because it does affect things. So recall as part of the definition, for something to be an eigenvalue of a matrix, it's not enough that it satisfies your basic ax is equal to lambda x. Even further, the creation of this equation means that the very solution x itself is non-trivial. And that little clause is easy to forget in there, but it is the very clause that prevents this from leading to catastrophic internal logical paradox. Okay? So we need this to have a non-trivial solution. So it is not sufficient, if you're doing a definition statement, it is not sufficient to merely say ax is equal to lambda x. Because if you're saying ax equals lambda x, okay, whatever, right? That always has a solution. 0 is equal to 0. So we clearly care only about non-trivial solutions to whenever we check an eigenvalue. So that means, by definition, if I do ax is equal to 0x, it's not just ax is equal to 0x, it's specifically ax equals 0x has what? At least one, yeah, so a non-trivial solution. Do you see the difference? Do you see the difference in precision and why this is going to be really, really helpful to clarify? Because when we do simplify, yes, this is as we think it should be. Ax is equal to the 0 vector. And suddenly stating that ax is equal to the 0 vector has a non-trivial solution packs a lot more meaning than just saying that I have a homogeneous equation. As a non-trivial solution. So to claim that 0 is an eigenvalue of a matrix is to claim that the homogeneous equation has a non-trivial solution, which is precisely the opposite statement of only having the trivial solution, right? So this is like logically, by statement, the opposite of invertibility. So A is not invertible. Because, and I'll do a little, recall in your dream. Recall that the statement A is invertible is logically equivalent to the statement that the homogeneous equation has what? Do you guys remember this from invertible matrix theory? Has only the trivial solution. So do you see how the statement has a non-trivial solution for this is the logical opposite of ax equals 0 has only the trivial solution? Okay? So going from this statement to concluding that A is not invertible should make sense then, right? Because if it's the opposite logically of this, it has to be the opposite logically of this. Perchance. Yes, Rebecca?
Does that imply that A has a null space without the involvement of any eigenvalues?
Okay, so you're asking if A has a null, so the null space of A.
If A has 0 as an eigenvalue,
Okay.
does that mean A also has a null space that's not just the 0 vector?
Well, right, yeah, because if the homogeneous equation has non-trivial solutions, then that means you have at least one free variable in there. So you'll spit out, yeah. Perchance. Okay. Extra credit for putting perchance at a random point of your proof in a humorous way. Actually, that's a joke. That's a joke. Don't do that.
Will there be points taken away?
There will not be points deducted. There we go. I can say it that way. You will not
I'm gonna write for changing.
Okay, this is the last little theorem here. If I have a set of vectors v1 through vr, and not just any vectors, but if these are eigenvectors, yes, that's an R, that correspond to distinct eigenvalues lambda 1 through lambda r of an n by n matrix A, then the set of vectors v1 through vr that we started with, if taken as a set, we can call it linearly independent. Again, the intuition and kind of blueprint for the proof here couched in this invertibility language, right? In the invertible matrix theorem. But yeah, so this is a big one though. If 0 is an eigenvalue, if you can find out that 0 is an eigenvalue, then your matrix is not invertible. Now, if you're dealing with some sort of a triangular matrix, and you want to see if this echelon form is invertible, that is a 1-second test. You look at the diagonal, and so long as none of those diagonal entries are 0, you are in fact going to be invertible. If there is 1, 0 on your diagonal, boom, gone, it's broken. It's not going to be invertible. But you already knew that, because when we did the determinants, and you go down the diagonal of a triangular matrix, what did we say? If you multiply them together, and your determinant spits out 0, you are not invertible. You see how all of these things are reaching the same exact logical conclusion. And it's all coming from these triangular forms. Okay, so think about that, maybe start the homework, and then Wednesday we'll actually progress more into why we kind of care about these things, and then build into the characteristic polynomials, okay?